Back to video lecture series on sensors and actuators. So in the previous module 1 and 2, we have seen the introduction to sensors and how to classify the sensor, what are the characteristics of sensor, and what are the applications and where we can apply the sensors, and how to find or how to select the sensors based on its characteristics. These are all we have seen in the module 1, and in module 2 the sensor is classified as two cases. So in the first case we have seen all the mechanical and electromechanical sensors. So now in this module 3 we are going to see the classification of sensors, second category, that is thermal sensors. So in thermal sensors we are going to see what are the different methods used for this thermal sensor, and what are its classifications. And apart from those thermal sensors, we are going to see radiation sensor, then magnetic sensor, and the very important sensors we are used in our day-to-day life and in our emerging technology is the smart sensor. So all these things covers in this module 3. So let me start with the thermal sensors. So already I told we have seen different types of sensors like electromechanical sensor, then mechanical sensor, yes, and then we have seen ultrasonic sensors, all these. So all these sensors will detect something from the physical parameter, or based on the physical property it may change. Similarly in thermal sensors, based on we are going to detect the temperature, that we can understand from the name itself, thermal sensor. So how to detect the temperature? So what are the ways we can detect the temperature? So here we have certain principles. Based on the principles, the sensors can be classified. So what are those principles? One is the material expansion. Due to material expansion, the temperature may change, and due to resistance in the resistance changes, the temperature may change, and due to the effects. What effect is thermoelectric effect? So due to that, the temperature may change. So these are the three different categories we can categorize in the thermal sensor. One is the material expansion type, and next one is the resistance change type, and third one is the thermo EMF type. So before we are going to these three classifications, first we should know what is a thermal expansion in thermal sensor. So thermal expansion is nothing but expansion. It will expand. When a temperature is applied, there will be some expansion will takes place. So what type of expansion? So if it is a solid case, how it gets expand. If it is a liquid, how it's expand, and if it is a gaseous, how it expands. So it will changes its shape. Shape may change, area may change, and volume may change as the temperature changes. So this effect we call it as thermal expansion. So based on these principles, we are going to categorize the classification as material expansion type. That is the first category. So in material expansion type, we have the expansion based on the solid, liquid, gases, and vapor as well. So first let us see with the solid expansion. So in solid expansion, here what the principle we have used is when solid is heated and when it is cooled, what happens? What happens to the solid when it is heated and cooled? So here we have we have a type called the solid expansion type, that is bimetallic strip. So bimetallic strip, we have two different metal strips or joined together. One end is fixed, another end is free, and each will have the different coefficients. So each metal, when we are heated, based on the coefficient, it may expand. Okay, so here we are having two different metal strips are joined together, and they are expand at different rates. So that we call it as bimetallic strip. So here I have taken a bimetallic strip. So these two strips is joined at one end, another end is free. So now when the strip is heated, what will happen? It will, based on the coefficient of the expansion, some may get very quickly to get expand. So one of the bimetal will expand and it bends towards. Here I have two strips. One, due to temperature, it gets expand like this. Okay. So this is the normal position. From this position, it gets expanded up to this. So this deflection gives the will be calibrated to the changes in the temperature. So this method we call it as solid expansion. So when a temperature is applied, so some metal will gets bent from the original portion, how much it gets bent. So that deflection will be calibrated to the temperature changes. So this is the material expansion type in solid case. And next one is the on how the so when it changes, what will happen? Automatically the length get changes, right? So the change in the length is given by alpha L into del T, where alpha is the coefficient, what material you are using, and L is the length, actual length. From the actual length due to temperature, how much it gets varied. And del T is the changes in the temperature. So from this we can find the del T as well, and also you can find the change in the length. So how much amount of change in the length happens, that much amount of temperature will be changed. And the next one is the liquid expansion. So when a liquid is heated at for certain temperature, how the liquid gets expanded. So here, this is the one of the oldest method, and it is a very simplest method and the traditional method we are using nowadays. And we can use the temperature range from minus 200 to 600 degrees Celsius we can use for this liquid expansion. So these thermometers are used to measure the temperature without any additional equipment. Additional equipment is not at all needed. So how we are going to read the temperature using our naked eye, we are going to measure the temperature, but this method is not that much accurate because this may give some error sometimes. So by seeing the naked eye, it may the vision may change by from different users. Okay, so this is one of the oldest method we have for the liquid expansion. So this is the mercury in glass thermometer. This is the glass. This is the glass thermometer. So inside you have a thermometer is placed inside the glass bulb, and this is the safety bulb as well. And inside that capillary tube, it's filled with mercury, and this is the temperature sensing bulb. So when you place this in a water tub, and as the water gets heated, what will happen? As the temperature increases, the mercury it gets expand and it start rising. So how much amount of start rising from the original, that will be, we can measure what is the temperature at this point of time, what is the temperature that we can see from the scale which is given in the glass bulb, which is attached to the glass bulb. So this is a traditional one, how temperature is measured. When you go to doctor, where olden days they used to keep a thermometer inside your in the tongue. So as the temperature increases, based on the temperature in our body, the mercury will expand, and from that we can say that what is the temperature. So this is the another method in liquid expansion. And third one is the gas expansion. So in gas expansion, we are using the temperature for the gas. So there you have a capillary tube, and so when the capillary tube is placed in a bulb, and one end of the limb is connected to the mercury thermometer, and another end of the limb is open to the atmosphere. So this is connected in a U-tube manner. So it acts like a U-tube. Okay, so when you're heating limb B, you have limb 1 and this is limb B. Okay, so as the temperature, so inside the glass bulb, you have hydrogen and helium gases are placed. So when the temperature increases, the gas inside the capillary tube will move into the U-tube, and already it will be set to some 0 point. As the temperature increases, the gas will expand and the gas will move from 0 to some point. So this deviation will be calibrated to the changes in the temperature. So this is the method used for gas expansion. And next one is the vapor expansion. So in vapor, as we have seen the previously, there you have a YouTube manometer, but here you don't have YouTube one, but instead you have the Bourdon tube. So this is your this is the bulb. Here you have a volatile. First you have the non-volatile fluids, and this is the volatile fluids are placed, and capillary tube is inserted into this bulb, and another end is it is a Bourdon tube. One end of the capillary is connected to the Bourdon tube. Another end is connected. It's a free end that is connected to the indicated scale. Okay. So now when the temperature increases, what happens? The volatile liquids will immediately it will change its as the temperature increases. What will happen? The volatile liquid will immediately it gets into vapor. So as the temperature increases, what happened? The vapor will pass into this capillary tube, and as the vapor increases, what happened? This Bourdon tube will changes its shape. Okay, and as the pressure, as the vapor increases, what happened? Already it is in this deflection. As the vapor increases, it may move based on the temperature. It will produce some deflection. So here in all the solid, liquid, uh, gas and vapor, how much amount of it gets deflected, that will be calibrated into temperature changes. So these are the different methods for material expansion: solid, liquid, vapor and gas. The next type of thing is the resistance change type. So these sensors, so in the name itself we can understand, as the temperature changes, there is a change in the resistances. Okay, so how much amount of resistance changes, that will be calibrated into a temperature. So here the method used is the thermoresistive temperature measuring devices. A change in the temperature, it will cause some electrical resistance of the material due to the changes in the temperature. So the resistance change is measured to infer the temperature. How much amount of resistance changes, that much amount of temperature will be inferred. So here there are two types of thermoresistive measuring devices. One is the RTD, resistance temperature detector. Another one is the thermistor. So now coming to RTD, resistance change type, we have used, these are the RTD materials are used, which will be when a temperature increases, due to the material which what we are using for this makes the resistance to change. So the common thing is, one common material used is the platinum. It's most widely used. It will has the temperature of 1000 and 100. And when you nickel, it's less stable only, but than the platinum, but it's cost effective. And copper, it has only the limited range of temperature. And other alloys like tungsten, balco, this is also we can use, but most probably we use only the platinum because it can use the temperature range of -200 to 850 degree Celsius. So this is the RTD, continual constructions. So it is this is the platinum element. So this is the platinum element. This is surrounded by the porcelain. This is the porcelain insulator. Okay, porcelain insulator. This is the platinum. This is surrounded by the porcelain insulator. So the use of this insulator is, it will prevent this short circuit between the, this is the sheath. Okay, inconel sheath and the wires, platinum wires. And usually we use the inconel. Inconel is nothing but it is a nickel ion chromium alloy. It is always used for the manufacture of the RTD, and it is used to protect the internal RTD sensing element and the lead wires. This is the lead wires this is the sheath. This is the insulator, and this in between this you have the inconel sheath. Okay, this is placed inside the RTD. So when you're keeping this RTD in a, you can have a different types of RTDs. When you place it in a water, as the temperature increases, what will happen? The platinum which is placed under the This is to be inserted in the water. So as the property in the platinum changes with whether we are heating or cooling, there will be a change in the resistance. So how much amount of change in the resistance happens, that will be calibrated to the change in the temperature. So the resistance of the RTD is given by RT equal to R naught into 1 plus alpha T, where alpha is the temperature coefficient and R naught is your resistance 0 degrees Celsius and RT is the resistance at some temperature, and capital T is the temperature in degrees Celsius. So here this RTD we call it as the positive temperature coefficient, because as the temperature increases the resistance value also increases. If the temperature increases and the resistance value decreases, then we call it as the negative temperature coefficient. So there are different types of RTD. One is the tip sensitive RTD. So the tip sensitive RTD, this is the tip sensitive. Okay. So the probe of sensing tip is constructed of the copper alloy. This is 20 times more conductive than the stainless. So instead of stainless steel, if you use this, it is 20 times it's more conductive. And these sensors will react more quickly and indicate tip temperature instead of temp. So mostly they'll use a stem type of RTD. We can also have a tip type. So the tip type is very quickly it will conduct when compared to the steel. So that we can and also improve the accuracy. So the application, I can say this used for surface temperature measurement of pipes, plates and machinery, and in food processing for monitoring the temperature we can use this tip sensitive RTD. And next one is the stem sensitive RTD. This is mostly used in all the industries where we can find the boilers and heat exchangers. And if you want to use for this large storage tanks, storage liquids, then we can go for this stem type of sensitive RTD. This entire length is the entire length of the sensor. It will contribute the temperature. This entire length will contribute that everything have to dip into this. But for the previous cases, it is not, we need not to dip entire, but here we need to dip the entire thing. So in boiler and furnaces, we can use this stem type, and heat exchangers also. And if you want to store a liquid in a large tanks, then you can go for the stem sensitive. So next comes the thermistor. Thermistor is nothing but is a combination of thermal and a resistor. So it is nothing but metallic oxides that is pressed. It is be pressed and it make it as a, it may be a bead shape or a disc shape, or as maybe a cylindrical shape. There are different types of shapes, and this comes in the category of negative temperature coefficient. That means the resistance will decreases with the increase in the temperature. Whereas in RTD, as the temperature increases, the resistance is also increased. Here, as the temperature increases, the resistance will decrease. So that we call it as negative temperature coefficient, and this is the symbol for the thermal resistor. So there are three, based on the material, it is classified in three types. One is the bead thermistor, disc and chip type thermistor, and next one is the cylindrical thermistor. The first one is the bead thermistor. It is manufactured with the shape of the bead. This is the shape of the bead. It just has the metallic wire connected to the ceramic body. This is the metallic wire. Okay, here you have the beads, and this is the connection for the for measuring the temperature. Okay, and this gives the better stability and also the quick response time, and it will protect from the mechanical damage, because there is no, as they are closed with this, there is no mechanical damage. It is smaller in size and have a very quick response. Very small only, but the response is very faster. It will be used in all the medical applications for measuring the body temperature. The next one is the disc and the chip type. This is the disc type thermistor. The body, the shape in the form, it is the form of the chip, and here you have two cables. Okay. So it has a larger metal surface. So since it has a larger metal surface, it has a lower response time. The response time is very lower. but it has a higher current handling capacities when compared to the B type, and is used in all the electronic circuits with wherever you want the high initial current, then we can go for this disk and chip type thermistor. And next one is the cylindrical type. So the thermistor body is pressed into cylindrical shape. So based on the shape, we have to press accordingly. And it has a larger shape when compared to bead as well as the disc type. And it is robust and reliable. And these probes are used for the general purpose applications for skin responses or skin sensors and battery temperature sensing. We can use this cylindrical thermistor. The next one is the glass encapsulated thermistor. So here the thermistor is sealed in a glass body. So already everything we have it as it is. Again, it has to seal with some glass body to improve the operating temperature. Okay, and these can be operated at the range of 150 degrees Celsius, above 150 degrees Celsius, and it is highly durable and moisture resistant. It is used for body temperature monitoring and for maintaining the temperature accuracy in our AC and cold storage. So next comes the radiation sensor. So far we have seen all the thermal sensors. Now we switch over to the radiation sensor. So the radiation sensor, the devices, so you know can understand from the name is radiation. So based on the different types of radiations, the radiations may be it may be electromagnetic radiations, or it may be nuclear radiations, or it may be thermal radiations. Based on the radiations, it will detect the based on how much amount of radiation falls on it, it will detect those radiations and it will convert it into current. So based on what applications we need, it will be changed accordingly. So it will devices that detect and measure the different types. So whatever the radiations comes, it will measure all those radiations. So types of radiation sensor, one is the optical radiation sensors. So in this model, you're going to see only the optical radiation sensor. One is the light dependent resistor, that is LDR, and then next the photodiodes, and next one is the photovoltaic cell. So the first one is the LDR, light dependent resistor. So in all the wherever we have nowadays, if you want to switch off the lights continuously, so nowadays they're using LDR. Whenever the person comes, it will sense and it will produces them lights. Okay. So with this LDR is also known as the light dependent resistor. It is a passive electronic component. It will detect the light from the environment. So it's based on the works based on the principle of photoconductivity, which is nothing but converting the lights into electrical signal. So that can be measured. Okay. So the LDR, this is made of this is the photosensitive semiconductor. Photosensitive semiconductor is nothing but maybe cadmium sulfide or lead sulfide or lead selenide or indium antimonide or cadmium selenide. These semiconductors are placed in a zigzag. You can see the zigzag pattern, zigzag manner, and you have two metal contacts are placed at the both the ends of the zigzag pattern, which helps to create a connection in the LDR. And among this zigzag manner, there is a transparent coating is placed, that is sand coating like silicone or epoxy resin or quartz, that is applied on the top so that the zigzag pattern shape it gets protected. So whenever the light falls on it or whenever it captures the light from the outer environment, this can be protected because it is a transparent layer. Since it is transparent layer, whatever the light falls on it, that can be easily absorbed by these semiconductors. So for that, we need that coating, transparent coating. So it works on the principle of photoconductivity. Whenever a light falls on the photoconductive material, that is like cadmium sulfide, so what happens? It absorbs the energy, and the electrons in the photoconductive material that will move from valence band to valence band, it gets excited and it moves from valence to conduction band. So when it moves from valence to conduction band, automatically there will be a flow of current, will flow of electrons. Due to the flow of electrons, there will be a electron flow or current flow will happen. So the energy in the instrument line should be greater than the band gap. Energy, whatever the energy which is passed, that should be greater than only the valence band, the electrons in the valence will be get excited and move to the conduction band. So automatic lights that switch on and off according to the light. Yes, it will be automatically switch on and off. For that we can use this LDR. And for alarm and for clock with automatic light and solar street lamp. Nowadays they are using as the solar street lamps. And in camera light, you're having a camera light, right? That is also this LDR. So next comes the photovoltaic cell. So photovoltaic cell is a nothing but a PN junction diode. So this is also converts the light energy into electrical power. So here it has three categories. One is the top layer, and second layer is the emitter layer, and third layer is the base layer. So the top layer of this PV cell is always a transparent conductive material. So what the material they have used is indium tin oxide is used, or we can use the dipped tin oxide also. Both can be used for this PV cell. So this it is nothing but a transparent conductive material, right? So the transparent material, whenever the sunlight falls on it, it is easily passed to the next layer. So for that we are using this transparent conducting layer. So beneath that, next we have the emitter layer. So this is the heavily doped N-type silicon. N-type silicon is heavily doped, and this is used for the movement of the electrons that will be generated and absorbed by the sunlight. And the third layer is the base layer. It is slightly low doped with the P diode or P-type semiconductor, and this layer is creating an electric field within the cell by providing the positive charged holes, because there you have more number of electrons, here you have less number of electrons but more number of holes. So this will form a PN junction diode. So whenever a sunlight falls on it, what will happen? It will be passed into the transparent layer, move to the next layer, that is N and P. So this you have P and N type, so that we form a PN junction. So this forms an hole and electron pair. So here the energy gets excited, energy gets generated, and the electrons in the valence band will be excited and moves towards the conduction band and providing an electric current flow. So this is otherwise we call it as PV cell is otherwise called it as a solar cell, because it's convert the sunlight into an electricity. So that's why we call this as solar cell. Okay, so the generated direct current can be used directly, or we can convert that into alternating current used for the inverters in our household applications or any industrial applications. So next one is the photodiode. So the photodiode here also it will is to convert the light into electrical energy. Okay, so here you have three. Here also you have the layers. So one is the P-type layer, and next one is the heavily doped N-type silicon. You have two regions, P and N-type. So it's also similar to the previous cases, but here since you have the more heavily doped of the silicon here, so whenever light rays falls on the diode, it produces a electron hole pair. That means inside you have the photoelectric effect. Inside you get the photoelectric effect. So whatever the light rays which is absorbed, that will be erased into the depletion junction, and these carriers are removed from the junction by the inbuilt, already you have the electric field of depletion. So the holes in the P region and the electrons in the N region forms a hole pair, and the same process what you have seen. The and the valence band gets excited, and the electrons from the valence will be moved towards the conduction band for the flow of current. So in that way, the photocurrent will be generated. So this will be used in optical sensors, then medical instruments, and other communication networks. You can use this photodiodes. So next comes the magnetic sensors. So in radiation sensor, based on the radiations, how you are generating the current. In magnetic sensors, it is a device that is used to measure the magnetic field. It will measure only the magnetic field, and that magnet will be and providing electrical signals that's corresponding to the field strength, direction, and changes in the magnetic movement. So these sensors are used in industrial, automotive, biomedical, and consumer applications. So the magnetic sensor is used to measure how much amount of magnetic field is present in the present, and based on the magnetic field, how it's converted into a electrical signal. So that is what magnetic sensors. And in that we have a method called the Hall effect. So Hall effect is already I have studied in the 12th standard. So when you have a current carrying conductor here, so here I'm going to place one magnetic field perpendicular to this current carrying this. What will happen? So when a magnetic is perpendicular to the carrier, perpendicular to the conductor, it produces some force. Some force will happen. So that force is called as Lorentz force. So this force will create an voltage. So that voltage we call it as Hall voltage. So now we are going to see a Hall effect sensor. So here you can see this is the conductor. It's a p-type semiconductor. We can call it as a Hall element. And magnet is placed perpendicular to this coil. So whenever a magnet is placed perpendicular to the conductor, what will happen? This conductor has all the positive charges and will move to one side, and all the negative charges will move to the other side. And uh, these charges, it produces a difference, produces a potential difference. So that we call it as potential voltage. The voltage is developed in this Hall element is called as Hall voltage. So next comes the smart sensors. So when what so far you have seen only all the different types of sensors, how we can use, and what are the applications, and how it works. So now we are moving to the next, moving to the forward, and whatever we need in our current situations or current technologies is the smart sensor. So it is an advanced sensor. The sensor, it has an integration of all the integrate of the sensing element with data processing, then communication is there, and decision making all together integrated and form a sensor, and this is called as smart sensor. So in traditional sensors we have to analyze the data, then filter the noise, then go for calibration, and then communication with the real time. Okay, but the smart sensors we have, now we have a IoT, that is Internet of Things. It will automatically, from anywhere, wherever you want, anywhere we can control this. So in home automation, all the automation things we gotta have this smart sensors. So everything is smart nowadays. So these smart sensors are used in automation, then healthcare industries, healthcare, then environmental monitoring, and in industrial applications. Nowadays, it plays a major role in all these areas. So the smart sensor, it has the following components are present. One is the sensing element, then signal conditioning, microprocessor or microcontroller, then communication module, and then power management. The sensor. So what we do in previous cases, the sensor will sense. After it gets sensing, it converts into electrical. That's all. Okay. But now in smart sensing, you have a sensor element is there, it will capture all the different types of signals and it's converted into an electrical signal. How it gets converts? Because whatever the signal is gets captured, these capture signals, it may have some noise. So what you have to do, we have to signal conditioning. Signal conditioning is nothing but we have to filter those noises. After filtering, the signal is of very weak signal, so we need to amplify the signals. After amplifying, suppose the analog signals may be converted into digital signals, so we need some signal conversion, so we have the signal. So this will be comes as an output when after using the signal conditioning. So the sensor, whatever the sensor output we get, that will be filtered, amplified and converted into a processed sensor data. That is what we get. Those sensor data, the next step is going to the controller. So here we are using the microcontroller. So it will process the sensor data. It will use some different algorithms. So nowadays we have the artificial intelligence. So using those algorithms, it will just process all the data which comes from the sensor. So after the microprocessor process the data, the next one is we need to communicate. So we have to transmit the data as via maybe a Bluetooth with wired protocols, or it may be a non-wired or wireless protocols. After it transmits the data, then we need to supply and optimize the energy, how much amount of energy it's used, that we need. Power management is very important. So this completes, we have the smart sensor. So we'll see one by one what is sensing element and others. So sensing element. So sensing element is nothing but it detects the physical, chemical or biological and converts them into a electrical signal. So I can use, or I can also use some sweat sensor. So sweat sensor, it will sense the sweat and converts into some signal. So for sweat sense, how it sense the sweat, it is nothing but the biological. Okay, so it may be anything. It is not only the physical form. It may be any chemical. Chemicals also we can convert into electrical one, and we can also use the biological, whatever it may be, it will sense and converts into an electrical signal. So here the sensing environment, it generates an analog signal. So the sensing element, it may be analog signal in the sense it may be a temperature sensor or pressure sensor, motion sensor, optical sensor, or we can have a chemical sensors for chemical properties, and for biological sensor for biological things. Okay, so we can use any types of sensors. So the sensor will sense and gives the signal. So next comes the signal conditioning and data acquisition. So data acquisition means signal conditioning is nothing but whatever the signal that comes from the sensing element, it undergoes some further process. One is the amplification, because if it is a weaker signal, it will boost the signals. And next one is the filtering. If the signal has more of noise, then it removes the noise by using low pass filter, high pass filter, band pass filter and band reject filters. After filtering the signal, the next we need to convert, because we're not going to process with the analog signal because everything is digitized now. So we need to do conversion, that analog to digital conversion. After converting from analog to digital, then because we are going to send the data to the microcontroller, it accesses only the digital data, so we need that conversion. And then if there is any variations in the sensor, then we need to adjust or we need to calibrate. So these are the steps we are using for the signal conditioning. Data acquisition is acquiring the data from the sensor and do all these process. So that is, in data acquisition we have all these noise filtering, and then converting the signal will happen in data acquisition layer. And next comes the processing and intelligent layer. The processing in the sense the microprocessor. So this is the brain of the smart sensor, because it undergoes data processing and then decision making. Because whether the sensor it gets correct or not, it will give some decision, because it has to give some control action to the next step. So this is the main part. If it doesn't work properly, it will not give a proper control action. So it will what the functions used in this processing is executes the sensor fusing. So if you have a multiple sensor, so it will execute which sensor is needed. So the controller will decide which sensor is needed for right now. So that particular sensor will be enabled. And next one is apply machine learning for smart decision. So to make the decision making, it uses the machine learning algorithms and detect anomalies and patterns in the sensor data. If there is any anomalies are present in the sensor data, it will detect, and it will self correct, enable self calibration or self correction. It's automatically it will correct. If you're using some automatic controllers, then whatever the error comes, it will automatically correct it and gives the and process the values and give us to the next step. So for that we are using microcontrollers, microprocessors and edge AI processor. So all these things are used for microcontroller we used for low power processor for embedded applications. For Arduino ESP32 we can use this, and microprocessor for Raspberry Pi and NVIDIA we can use this microprocessor. For edge AI then you have to use for the Google Coral, Raspberry Pi kit as well. So after the microcontroller, next one is the data which is processed will be communicated. So the communicated may be in the form of IoT platforms, or it may be cloud. We can save transfer data through cloud, or maybe any controlled devices. So it sends the data to the cloud or smartphone or the local servers. We can also use a wire or wireless protocols for connectivity, and it supports the edge computing for reason is to minimize the data transmission. So these are all some of the examples for the wired protocols. I2C, that is integrated circuit. It is used for the sensor for MCU communication. And SPI is a serial peripheral interface for high speed sensor communication. We can use this for SD cards and other displays. We can use this. And UART, universal asynchronous receiver and transmitter. It is for the serial communication for debugging the sensors like GPS modules. And CAN bus, it is used in all the automotive and industrial applications. These are all some of the examples of the wired protocols. And wireless protocols, you have Wi-Fi nowadays, ESP32, these are all Wi-Fi module. So it will take the IoT data transmission to the cloud servers. And then we can also have the Bluetooth for wearable and other medical devices. We can use this Bluetooth connection, and Zigbee for smart home automations, and LoRa for large range. LoRa means large range of IoT applications. We can use this LoRa, and 5G for high speed. Nowadays we have this all 5G networks. These are some of the communication network. And next comes the power management. So here this unit, so whatever the sensor operate, whether the sensor operates efficiently with the minimum consumption is it's needed, right? If it is sensor operates with the maximum power means it's of not used. So we have to check always the sensor is used with a minimum power consumption, and we need to extend the battery life as well. So we have used the following functions. So manages the power supply. We can use battery. We can use or AC or solar. We can use solar. So optimize the energy usage with sleep modes and implement the energy harvesting for self-sustained operations. So the power sources and the components we can use the rechargeable batteries or use, that is lithium ion battery and lithium or lipo batteries we can use, and we can also use the solar panels more advisable used in remote environments, in remote areas. We can straightly use this solar panel. And next comes the energy harvesting techniques. So we can use the piezoelectric, thermal electric and energy, RF energy harvesting. So far we have seen all the thermal sensors, or other different types in thermal sensors, then in radiation sensors, what are the different types we used in the radiation sensor, then magnetic sensor we have seen, and finally we have seen the smart sensors. So I hope you all have understood the concepts of all the sensors in this module. I hope you all enjoyed this video. Meet you in the next video series in module 4 of sensors and actuators. Thank you.